Hi, and welcome to the Code Maven's meetings and the Code Maven channel if you're watching it on YouTube. My name is Gabor Szabo. I usually teach Python and Rust and help companies with these two languages mostly. And I also organize these events because I really like the idea of sharing knowledge. Receiving knowledge from other people, like this time Tomer, and from around the world. So that's a good idea, I think. And that's it. If you're watching the YouTube, then please like the video and also follow the channel. And thanks everyone who arrived to this meeting, and especially Tomer for giving us the presentation. Now it's your turn. So welcome.
Okay.
Please introduce yourself and yeah.
Thank you. Let me share my screen. Okay. Can you see it?
Yes.
Excellent. Okay. So first of all, I have to make a confession. It wasn't 6 lines of code. It was actually 7 lines of code. And I guess you're all pretty wondering, curious what these lines of code were. So here they are. Okay. It was 8 lines of code if you count the space in between the functions. And we'll dive into what exactly these lines of code mean a bit later and why these allowed us to save so much memory. But first of all, just so you believe me, this is our memory usage graph in production when we deployed this fix. As you can see, the deployment was around 5:10 p.m., which is a great time to deploy fixes. If I remember correctly, this was a Thursday, which is the end of the week for Israel. Perfect time for deploying to production. But first of all, do we have anyone in the call who happens to be a US citizen or has to file US tax reports? Feel free to wave or something if there are.
Yeah.
I guess not. Well, if you were, I guess this would probably look pretty familiar to you. So for those of you who don't know, practically all US citizens are required to file tax reports annually for the IRS for their income taxes. This is a pretty painful process. It requires filling out a lot of obscure forms. And if you make some mistakes on it, you can find yourself in jail. So most people either pay one of the existing companies who provide services for filing tax reports or pay an accountant to do the tax reports for them. So hi, my name is Tomer. I'm the tech lead at April, and we are fixing the issue of IRS tax report filing. We are developing a simple to use application that allows users to file their taxes seamlessly with the IRS. Usually takes most users around half an hour to do their taxes, which is pretty awesome compared to what it normally takes, which is many hours. And and we don't charge them nearly as much as an accountant or one of the existing providers charge for this. If I look a bit tired in the recording, I'm going to let you guess which one of these are to blame today. Hint, she's on the left. She's 6 months old. I live with my partner and 2 kids in Givatayim, which is a suburb of Tel Aviv, and our dog. But I guess you're not here to hear about me and my life. You're here to hear about performance in Python. So let's dive in. Our story begins when we notice there's some certain action in our system that's taking quite a long time to complete. In fact, we even got some reports from users complaining that they were hitting timeouts when they were running this specific action within the system. And I was assigned to this task, started digging in, and I managed to reproduce it locally. I created a nice little script that created exact conditions of the users that were timing out. And the first step was to see how long it actually takes. And yeah, it was actually pretty slow. Python comes with a couple of built-in modules in the standard library that are pretty nice when you're timing things. There's time and there's time it. I will leave reading the exact documentations of them to the listener. But I actually have, it's very useful if you know what you're looking for. For example, if there's a specific method that you know is slow and you want to measure some change that you make to it and you want to see the impact of it, this is very useful. We even have a little wrapper method that allows us to easily measure the timings for various functions that we call. But what do we do if we're not sure where the slowness is coming from? This specific action in the system, this was a pretty complex action. It involved calling several different services, a lot of methods. So it's pretty difficult if you don't know where the slowness is coming from. So this is what profilers were invented for. Profiler, there's a TV series called The Profiler. We're not going to talk about it. I have no idea what it's about. But profilers generally come in two different varieties. There are that we will mention as we go. The first variety is deterministic profilers. These are profilers that essentially every time you make a method call, they register that method call, they write down the start time, and once that method returns, they write down the end time. Python standard library has a nice one called cprofile. It gives you a context manager. Basically, you wrap the code that you want to measure with the context manager, then call whatever slow function you want to profile and save the statistics to a file. And cprofile will actually take care of going over all of the method calls within that function, measuring how long they take, how many times each method is called, etc. And it saves all of these statistics into a file, which can be used, can be read using a module called pstats. Pstats allows you reading these files. And just so there's a lot of information here you can see. We'll dive into it a little bit to understand what this table is about. So first of all, on the right, we can see the file name, line number, and function name. Pretty basic, so you know what we're calling here. On the left-hand side, we can see the number of calls to each function. As you can see, the first three here were called just once. This is actually the script that I was using to debug this issue. The second column here is total time, which is the time that was spent within this specific method in total, all of the times that it was called. And there's cumulative time, which is basically the time that was spent within this method and any other method that was called from within that method. And something stood out pretty quickly to me. Out of 12 seconds runtime in total, about 6 seconds or half the runtime was spent in one specific method. And this method is ABC, subclass check. Interesting. Okay. Let's see. And even more interesting is the number of times this was called. So in 12 seconds, we actually called this method 175,000 times. That's the number on the right. And if there's a slash and another number here, that means that this method was calling itself recursively. So in this case, we were calling ABC subclass check a bit over 3 million times. So about 20 times for every single call that we were making to subclass check. It was actually making about 20 different calls on average. Okay, pretty interesting, but still I'm not quite sure why we're calling this method so many times, or why is it taking so long when this method is being called. And that's what the second type of profilers is really useful for. identifying. The second type of profilers is statistical profilers. These are profilers that basically take a snapshot of the Python call stack, or in any other language, the call stack every certain interval. Usually, this is done every few milliseconds. The shorter the interval, obviously, the higher the impact it has on performance. On the other hand, if you set too long of an interval, you might miss very quick method calls that return within the interval, and they won't actually be registered when running the profile. And a very common way of looking at statistical profiles is using a tool called flame charts. The way that flame charts work, basically you have two axes here. The x-axis is the time. So the bigger the block is on the x-axis, that means the longer time that was spent within that specific block. And the y-axis is the stack. So you can see the actual call stack of every single method. And you can see why it was being called, where the call was coming from, see the bigger ones, the smaller ones, and then that's very helpful when you need to debug and identify why a certain method is being called a lot of times. So I used one of these statistical profilers, specifically one called PySpy. There's multiple different profilers available for Python, and each language has its own ecosystem of profilers. I'm just showing the ones that I used in this case, but there are various other tools that are useful, and they are all good in their own fields. So I ran statistical profiler PySpy on this reproducer that I created. And yeah, okay, this is fine. This is fine. I can deal with that. As you can see, flame chart, when you have a very complex operation, can be very, very, very difficult to read. Sometimes there's something that stands out. You see a very big block that's taking a very long time to call, and you can identify the bottleneck pretty quickly from looking at this. But other cases, everything is on fire and you don't really know what's going on. Specifically in this case, we were seeing a certain method call being called 3 million times, which makes sense that it would be very difficult to identify all of these different calls within the flame chart. And for that, there's a nice tool called Sandwich, not that kind of sandwich. There's a tool called Speedscope, and it has a way of showing flame charts in a different way, which is, they call it Sandwich. Basically, on the left-hand side, we can see all of the different method calls within our application, within the run that was profiled. And we can sort this list by the total time and by the self time. This is the same, by the way, as we saw previously, total time and the cumulative time within cProfile. And then once you click on one of these, you can see on the right-hand side, those two parts. There's the callers and the callees. The top half shows you where this method was being called from. So for example, in this case, we can see subclass check was mostly called from instance check and some other internal methods. Also here we can see instance check was being called from various other methods. And here the x-axis actually shows the time that's cumulative by the specific method. So this isn't a single call, this is the total of the times that it was called from here. And obviously I can't share the internals of our system, but you can see that there were several places that we were calling instance check pretty commonly, leading to most of the load on this method. And on the left, you can see again, this was about 8 seconds in this test run. So quite a long time from the overall time. Okay, so instance check, subclass check. This is like built-in Python stuff, right? I mean, it's not something in our code base. What what should I do about it? It's pretty odd. I don't know. Let's I guess ask Dr. Google. And turns out there's an open issue about ABC subclass check, which has very poor performance and I think a memory leak. Memory leak? Interesting. Memory is pretty expensive. And turns out I'm pretty bad at counting. So there's not actually two kinds of profilers, there's three kinds of profilers. There's also memory profilers. Besides the runtime profilers, memory, obviously it's expensive if you need to use and allocate a lot of it, but it's also expensive in terms of performance because if the Python runtime runs out of memory, it has to make system calls to allocate additional memory to the Python program. The garbage collector also has to go over all of the memory and clean up unused memory. So the more memory you allocate, the slower the garbage collection will be. So these tools, the memory profilers, allow us to identify issues with our memory allocations. Sometimes our program can be very fast, but allocates a very large amount of memory. Just recently, we had a case actually where a certain process was crashing, and we were seeing pods being killed, so out of memory kill. Basically, in Kubernetes, when you allocate a certain amount of memory to a process, if the process runs over the memory, the Kubernetes controller will kill it, so it doesn't starve out other processes. And in this specific case, memory was running out so quickly that it wasn't even sending telemetry data to Prometheus. And we used actually a memory profiler to identify where exactly this memory was being allocated so rapidly that it was killing our pods. So let's talk about memory profilers a bit. There's a really nice one for Python called memory. It gives you some nice runtime statistics on your program. In this case, this is a reproducer script that I was using. We can see that we actually had about 11 million object allocations during the script. You can notice that the runtime here is a bit longer than the 12 seconds that it took when running with just cprofile, and that's because every single memory allocation that the program does, there's some overhead to it when you're profiling it. So the runtime was a bit slower here, and we were allocating nearly 2 gigabytes of memory when running this process. And it also gives you information like which Python memory allocator was being used, number of frames, that's the number of samples that it was taking. This is also a statistical profiler. And it also shows us a nice flame chart like we saw before. But unlike the runtime profilers, this flame chart, the x-axis is actually the size of the memory allocated. So the wider the block is, that means that the memory allocated within this block was higher. And also, we can see specific statistics for a certain method call. For example, in this case, we were allocating 82 megabytes of memory, and 2,500 objects were being allocated in a single call to subclass check. Okay, so let's go back to the bug. ABC subclass check has very poor performance, I think memory leak. It's open since May 2022. Anybody in the audience maybe knows who Samuel Colvin is? Feel free to unmute if you do. Anyone? So, Samuel Colvin, that's the guy behind Pydantic. Pydantic is a very popular data validation library for Python. He opened this issue almost 3 years ago, and it's still open. So, well, I guess case closed. Python is a slow language. There's nothing to do about it. We have to rewrite our application completely using Go, Rust, Elixir. I don't know, what are the cool kids using today? Gabo, I know you do Rust a lot. So I guess rewrite, right? No, I could just decide this is a case of language limitations. We have to cope with it and that's it. But I decided to dig in a little bit deeper and try to figure out if there's something we can do to resolve the issue. And to dig in a little bit deeper, we need to discuss ABC a bit, not the TV network, abstract base classes. For those of you who are not familiar with abstract base classes, which, as we mentioned, have a very poor performance for their subclass check. Abstract base classes is a mechanism in Python that allows us to define an abstract class, which allows us to define certain methods. We require any class that is subclassing from that class to do. We require these methods. So if we try to subclass it and we don't implement these specific methods, the interpreter will yell at us saying, hey, this class has to implement a certain method. Usually we use subclass ABCs as mixins, basically defining a specific interface we want to implement. But they have an interesting idea that is registering virtual subclasses, which is, for example, let's say you have a base class that you've defined, and you want one of the built-in types of Python to be a subclass of that. Obviously, you can't have int subclassing something else, right? And the ABC class or ABC meta subclass, ABC meta class, sorry, ABC meta class allows us to register various other classes as virtual subclasses of the base class. This is also useful if you have a class that implements multiple interfaces. Let's say you have a class that implements iterable and implements hashable and implements I don't know, sortable, say, and a few others. Obviously, you don't want to have to declare all of these when you create a class. You can just register this class as a virtual subclass. And that means that if you look at the method resolution order, the MRO of a specific object of that class, you won't see these classes as their parent. That's, by the way usually subclass check works. It checks the method resolution order to see if the parent class is there. But since we allow registering subclasses virtually to classes that aren't the actual parents, there's a specific implementation within ABC meta for subclass check and instance check that allows support for this specific use case. So just to better understand this use case, let's say we have this class hierarchy. We have a base class, which is an abstract base class. We have class A, class B inheriting from that base class. And we have a virtual subclass, which isn't inheriting from the base class, but it's registered as a subclass of this base class. And so forth. We have a virtual subclass A, etc., etc. Let's say we have an object and we want to check if that object is a subclass or an instance of base class. In this case, let's say this object is of type virtual subclass A. We would need to check the whole inheritance tree for base class to identify if this class was registered to any of the classes within that inheritance tree. So this calculation is pretty complex. There's also potentially an issue with a bad implementation of caching within the implementation of abstract base class. But normally this isn't a big issue because you wouldn't have that many classes inheriting from a single base class, maybe 2, 3, 10, 20. Usually it's not noticeable. But as I mentioned, we're dealing with tax reports and tax filing for the US IRS. There's thousands of different forms that the user needs to fill in. Think of the number of states. Each state has its own forms. Each form is composed of multiple different parts. And you can pretty quickly guess the rough number of classes that we have in our system to enable this fairly complex calculation, which has led us to this issue because of the very large inheritance tree that we have from our base class that we use for the calculation. And that's why, going back to the solution, this solution worked. Let's look at it a bit more in depth. Obviously, we're using type definitions. We're not barbarians. Previously, I was dropping them just to make it easier to look. But this is very, very straightforward. There's is subclass and is this instance. And what they do is they go to type. Type is the base class for all classes, in case you're not familiar with it. And they call subclass check or instance check on type directly. By default, when you call is instance or is subclass, the way it works is it goes to the class that is on the right-hand side of the second parameter, basically, of the function call, and it checks the meta class for that class, looking for subclass check or instance check, depending on which method you called, and then it goes up the method resolution order until it finds the implementation. In case of an abstract base class, it would go to abstract base class ABC subclass check. But here what we do is we basically bypass the ABC methods and go directly to the source type subclass check, which is the default implementation used by Python for any types that aren't abstract base classes. And then all we had to do in our code base is a very simple change. Use is subclass from fast subclass instead of using the default Python implementation. Checking if it's a subclass of the base model. And the reason this worked is because we didn't really care about the virtual subclass aspect of ABC. In our case, we were just checking if a certain object is or isn't a subclass of our base model. This wouldn't work, obviously, if we were actually registering our objects into the base model instead of directly inheriting from it. But in our case, this was good enough. And as you can see, there's another very nice added benefit to profiling. It lets you add nice statistics to your pull requests. For example, runtime went down from 33 seconds to 26 seconds. Memory usage was improved by 50%, etc., etc. Actually, I didn't even have to implement this in all of the places. I only had to switch to using the fast subclass in very specific places I identified using profiling as being the most common places that this was being called from. And this already gave me a very significant improvement. And when we actually deployed this fix, turns out that the impact was even higher than the specific use case that I was profiling. Because this had impact across the system, it could significantly, as you can see here, reduced our memory load. It also improved the system runtime in general, and also the system load time was drastically reduced, making our deployments much faster and saving a lot of costs. Questions, anybody?
First of all, thanks for the presentation. Can you go back one slide?
Yes.
What is this bump, the hump there?
That's a good question, actually. That's we're using rolling updates. So basically, we spun up a few pods, switched over to them, then spun up a few more pods, and this is the time when there were still some of the older pods running in parallel with the newer pods that were using less memory. So this is the first drop is when we killed the first batch of the old pods, and the second drop is when we kill the second batch.
But why did it? I still don't understand why it went up. Why did it go up again?
So we started a few pods, killed a few, and then started a bunch more, and then killed the rest. So,
Okay.
Yeah, this is just a loading of the new pods while the older ones were still running.
Okay, nice.
Any other questions, anybody? Okay, thank you very much.
No, it seems so. Thank you for giving this presentation, and everyone for being here and listening. And I'm going to stop the video, but please remember to like the video and follow the channel. And see you next time, Tomer.
Bye bye. Thanks for having me, Gabo.
Bye bye.